Hello everyone. If you're aiming to become Databricks Certified Machine Learning Associate, you are in the right place. I have gone through the newly updated official syllabus, summarized the key topics in detail, and compiled a comprehensive study guide to help you approach this exam. Please note that this content represents my own efforts and is not affiliated with my employer. Generally, I create my own notes, so I thought why not share my notes here as well, right? So let's get started on the journey to help you become certified.
Databricks Certified Machine Learning Associate Section 1. Databricks Machine Learning Databricks ML1. Identify when a standard cluster is preferred over a single node cluster and vice versa. Standard cluster, best for distributed workloads that require parallel processing across multiple executors. For example, large-scale data transformations, training distributed ML algorithms. Single node cluster, suitable for lightweight development, small-scale experimentation, or when using libraries such as certain single-node scikit-learn models that don't require distributed processing. Key considerations: cost optimization. Single node might be cheaper, scale of data, and concurrency. 2. Connect a repo from an external Git provider to Databricks repos. Prerequisites: ensure Git integration is enabled in your Databricks workspace. Steps: From the workspace click Repos. 2. Select Add Repo, then provide the Git repository URL. 3. Authenticate via personal access token or auth, depending on provider. Best practices: use branches to isolate development changes. 3. Commit changes from a Databricks repo to an external Git provider workflow. Make changes in your Databricks notebook. 2. Access repos. Right arrow commit and push. 3. Provide a commit message and push changes upstream. Key consideration: keep notebooks modular. Use meaningful commit messages. 4. Create a new branch and commit changes to an external Git provider workflow. In the repos, select branch, right arrow create new branch. 2. Make code changes on the new branch. 3. Commit changes to that new branch. Why branches matter. Branching supports parallel feature development without risking conflicts on the main code base. 5. Pull changes from an external Git provider back to a Databricks workspace process. In repos, select the repo. 2. Click pull or sync to fetch new commits and merge them. Conflict resolution. If conflicts arise, you may need to resolve them via the Git provider or by manually editing the notebook. 6. Orchestrate multitask ML workflows using Databricks Jobs. Databricks Jobs. Chain multiple tasks, for example, data prep, feature engineering, model training, evaluation. 2. Configure dependencies and triggers between tasks. Best practices: use job clusters for ephemeral usage, separate dev test prod workflows, leverage cluster reuse to save costs. Databricks Runtime for Machine Learning 1. Create a cluster with the Databricks Runtime for machine learning purpose. Leverage pre-installed libraries, scikit-learn, mlib, xboost, etc. and tuned Spark configurations. Steps: Go to Compute. 2. Create a cluster. Select Databricks Runtime version. Right arrow. Databricks Runtime for Machine Learning x.x. 3. Optional. Configure autoscaling, spot instances, or GPU usage. 2. Install a Python library to be available to all notebooks that run on a cluster. Methods. %pip install less than library underscore name greater than in a notebook cell. 2. Set up an init script or cluster library to install automatically on cluster start. Recommended approach: if the library is needed globally for your team, consider cluster level or workspace level library installation. AutoML 1. Identify the steps of the machine learning workflow completed by AutoML steps. Databricks AutoML 1. Exploratory data analysis, basic stats, data checks. 2. Automated feature engineering. 3. Model selection and hyperparameter tuning. 4. Model evaluation using standard metrics. Outcome: a fully trained pipeline, evaluation metrics, and code notebooks to reproduce the process. 2. Identify how to locate the source code for the best model produced by AutoML. Within the AutoML experiment, navigate to the best trial or best model link. Generated notebooks. Automil typically produces notebooks in your workspace with the model's training code. 3. Identify which evaluation metrics Automil can use for regression problems. Common metrics C, may, are circumflex 2, depending on the selected model type. How to check. Review your Automil experiment summary in the Databricks AI. 4. Identify the key attributes of the data set using the Automil Data Exploration Notebook. Data Exploration Notebook provides summary stats, distribution plots, missing value analysis, correlation feature importance insights, usage, evaluate data cleanliness, potential transformations, and overall readiness for modeling. Feature Store 1. Describe the benefits of using Feature Store to store and access features for machine learning pipelines. Centralization, avoid duplication, consistent single source of truth, versioning and lineage, track how features were computed over time. Collaboration, teams can share and reuse carefully curated feature sets. 2. Create a feature store table. Key steps. 1. Import the feature in store client. 2. Use create_table to define the schema, primary keys, and metadata. Best practices. Define appropriate data types, ensure consistent naming, and document the feature table's purpose. 3. Write data to a feature store table. Typical API. fs.write_table. Name equals table_name. df equals my_spark_df. Mode equals merge/overwrite/append. Considerations. Use merge to update existing rows by primary key. Overwrite replaces everything. Append adds new rows without updates. 4. Train a model with features from a feature store table. Workflow. 1. Use feature lookup objects in your training code. 2. Join features from the feature store with your training dataset. Benefits. Ensures consistent features, trackability, and reproducibility across training. 5. Score a model using features from a feature store table. Inference workflow. 1. Create a Spark data frame with entity IDs. 2. Use feature lookup to retrieve relevant features. 3. Apply your trained model's transform method or use MLflow to serve predictions. Managed MLflow. 1. Identify the best run using the MLflow client API usage. Query runs with search_runs. 2. Sort by a particular metric, for example, accuracy. 3. Select the run with the best performance. 2. Manually log metrics, artifacts, and models in a MLflow run code pattern with mlflow.start_run, mlflow.log_param_name, value, mlflow.log_metric, metric_name, value, mlflow.log_artifact, local_path_to_artifact, mlflow.sklern.log_model, artifact_path equals model. Why manual logging? Fine-grained control over what gets tracked and how. 3. Create a nested run for deeper tracking organization usage. Nested runs let you group related experiments, for example, for hyperparameter search inside a single parent run. Implementation. Parent_run equals mlflow.start_run. Child_run equals mlflow.start_run. Run_name equals child. Nested equals true. mlflow.end_run. mlflow.end_run. 4. Locate the time a run was executed in the MLflow AI. In the MLflow tracking server or experiment page, each run lists a start time and duration. 5. Locate the code that was executed with a run in the MLflow AI. If you enabled code tracking or used Databricks notebooks, you can often see the git commit or the notebook revision in the artifacts section or run details. 6. Register a model using the MLflow client API example. Result equals mlflow.register_model. Model_URI equals runs/run_id/model. Name equals my_registered_model. Purpose. Model registry fosters versioning, stage transitions, and better collaboration. 7. Transition a model stage using the model registry AI page. AI based. In model registry, right arrow select version, right arrow transition stage, right arrow choose staging or production. 8. Transition a model stage using TML client API code. Client.transition underscore model underscore version underscore stage name equals my underscore registered underscore model version equals version underscore number stage equals production 9. Request to transition a model stage using the ML registry page approval workflow. If governance is in place, you can request transition. Another user with appropriate privileges approves the transition to the new stage. Section 2, ML Workflows Exploratory Data Analysis 1. Compute summary statistics on a Spark data frame using summary syntax, df.summary. Show what it shows, count, mean, stdef, min, 25th percentile, 50th percentile, etc. 2. Compute summary statistics on a Spark data frame using Butyl's data summaries. Butyl's broken vertical bars. Some Databricks runtimes have butyl's.data.summarize df for quick stats. Usage offers a convenient graphical user interface based or notebook based summary. 3. Remove outliers from a Spark data frame that are beyond or less than a designated threshold. Typical approach. Broken vertical bar. Identify outlier thresholds via standard deviation. For example, mu plus minus sign 3 sigma pm 3 backslash sigma or ICR-based boundaries. Filter outliers with a filter or where clause in Spark. Threshold equals df underscore filtered equals df dot filter feature less than threshold. Feature engineering 1. Identify why it is important to add indicator variables for missing values that have been imputed or replaced. Reason preserves the information that the original value was missing, which might be predictive. Example, if age is missing, set age underscore missing equals 1 after you impute the missing value. 2. Describe when replacing missing values with a mode value is an appropriate way to handle missing values. Use cases for categorical features with strong class imbalance or if the mode is highly representative. Limitations might obscure underlying patterns if the distribution is not well represented by the mode. 3. Compare and contrast imputing missing values with a mean value or median value. Mean 1. Sensitive to outliers, easy to calculate. Median 1. More robust to outliers, but might not reflect actual distribution if data is skewed. 4. Impute missing values with the mean or median value. Spark ML. Use imputer with strategy equals mean or strategy equals median. 5. Describe the process of one-hot encoding categorical features. Process 1. Map each categorical level to a unique integer index. 2. Convert each index into a binary vector with length equals # categories. 3. One category is hot 1 while others are 0. Spark string indexer plus only hot encoder estimator. 6. Describe why one-hot encoding categorical features can be inefficient for tree-based models. Reason tree-based models can handle categorical variables differently and often do not need many binary dummy variables. One-hot encoding might create very high-dimensional sparse data that can slow down training. Training 1. Perform random search as a method for tuning hyperparameters. Random search randomly sample from a predefined range of hyperparameters. Benefits often more efficient than exhaustive grid search with a large search space. 2. Describe the basics of Bayesian methods for tuning hyperparameters. Concept iteratively uses prior results model performance to choose the next best set of hyperparameters to try. Benefit more efficient than random or grid search, especially for complicated search spaces. 3. Describe why parallelizing sequential iterative models can be difficult. Sequential dependence. Bayesian optimization or certain iterative algorithms rely on results from the prior iteration to decide the next configuration. Implementation complexity must ensure partial results are synchronized across workers. 4. Understand the balance between compute resources and parallelization trade-off. More parallelization right arrow more compute cost but faster results. Less parallelization right arrow cheaper but slower. Rule of thumb, start with moderate parallelism, scale up or down as needed based on performance and budget. 5. Parallelize the tuning of hyperparameters using HyperOpt and SparkTrials. SparkTrials distributes trials across the Spark cluster. Key pattern, from HyperOpt import fmin, TPE, HP, Spark drills trials equals spark drills. Best underscore hyperparams equals fmin. Fn equals objective underscore function. Space equals search underscore space. Algo equals TPE dot suggest. Max underscore evols equals 50. Trials equals trials. 6. Identify the usage of Spark drills as the tool that enables parallelization for tuning single-node models. Why it matters, even if your model is single-node. For example, scikit-learn, HyperOpt with Spark drills can run different hyperparam configurations in parallel on multiple executors. Evaluation and selection 1. Describe cross-validation and the benefits or downsides of using cross-validation over a train validation. Split cross-validation splits data into K folds, iteratively trains on K1 folds, validates on the remaining fold. Benefits: more stable estimates, better usage of data. Downsides: more computationally expensive. 2. Perform cross-validation as a part of model fitting. Spark ML. Use cross-validator with an estimator, param grid, and evaluator. 3. Identify the number of models being trained in conjunction with a grid search and cross-validation process formula. # hyperparam combinations times # folds. Example, if you have 10 combos and 3 folds, you train 30 models total. 4. Describe recall and F1 as evaluation metrics. Recall: true positive as true positives plus false negatives. Text: true positives / text: true positives plus false negatives. Measures how many positives you correctly identified. F1 score: harmonic mean of precision and recall. Good for imbalanced classes when both metrics matter. 5. Identify the need to exponentiate the RMC when the log of the label variable is used. Reason: if you trained a model on log y / log y, the predictions and errors are in log space. To interpret in original space, you exponentiate results. 6. Identify that the RMC has not been exponentiated when the log of the label variable is used. Pitfall: if you see suspiciously low RMC and you use log transformations, ensure you convert predictions back to the original scale. Section 3, Spark ML Distributed ML Concepts 1. Describe some of the difficulties associated with distributing machine learning models. Challenges: synchronizing gradient updates, large data shuffles, communication overhead, hyperparameter search complexity. 2. Identify Spark ML as a key library for distributing traditional machine learning work. Spark ML provides built-in distributed implementations for common algorithms, for example, linear regression, logistic regression, decision trees. 3. Identify scikit-learn as a single-node solution relative to Spark ML. Scikit-learn, great for local or small data sets. For big data, use Spark ML or distribute scikit-learn jobs via Spark Trials or JobLib. Spark ML modeling a piece 1. Split data using Spark ML method. Train_df. Test_df equals df.random split 0.8, 0.2, seed equals 42. 2. Identify key gotchas. When splitting distributed data using Spark ML gotcha, data might not be perfectly balanced in each partition. Always check distribution after the split. Mitigation: use a seed and random split carefully, or consider stratified sampling. 3. Train/evaluate a machine learning model using Spark ML workflow. Broken vertical bar: create an estimator, for example, logistic regression. Broken vertical bar: fit on training data. Broken vertical bar: evaluate predictions on test data. 4. Describe Spark ML Estimator and Spark ML Transformer Estimator, an algorithm that fits or trains on data and produces a transformer. For example, logistic regression. Transformer applies a transformation, for example, vector assembler or a trained model. 5. Develop a pipeline using Spark ML pipeline. Chain multiple stages: string indexer, vector assembler, estimator. Usage ensures reproducible transformations and easier hyperparameter tuning. 6. Identify key gotchas when developing a Spark ML pipeline. Common issues: broken vertical bar: not vectorizing your features correctly. Broken vertical bar: failing to handle new categorical levels at inference time. Broken vertical bar: overriding pipeline stages incorrectly. HyperOpt 1. Identify HyperOpt as a solution for parallelizing the tuning of single-node models, single-node, scikit-learn or custom Python models, distributed across a cluster with Spark drills. 2. Identify HyperOpt as a solution for Bayesian hyperparameter inference for distributed models, TPE. Tree structured Portson estimator is used under the hood. Benefit: more efficient search than naive methods. 3. Parallelize the tuning of hyperparameters for Spark ML models using HyperOpt and trials approach, similar to single node, but the objective function calls Spark MLs. Fit method. 4. Identify the relationship between the number of trials and model accuracy generally. More trials can lead to better hyperparameter exploration, but diminishing returns eventually. Pandas API on Spark 1. Describe key differences between Spark data frames and Pandas on Spark data frames. Spark DF, fully distributed, does not maintain row order, wide transformations. Pandas on Spark extends the Pandas API but under the hood uses Spark to distribute data. 2. Identify the usage of an internalframe, making Pandas API on Spark not quite as fast as native Spark internalframe. Manages overhead of mapping Pandas operations to Spark. Some operations may be slower than raw Spark transformations. 3. Identify Pandas API on Spark as a solution for scaling data pipelines without much refactoring benefit. If you have existing Pandas code, you can often switch to PySpark.pandas with minimal changes. 4. Convert data between a PySpark dataframe and a Pandas on Spark dataframe syntax. Import PySpark.pandas as PSPDF equals PS dot from underscore Spark, Spark underscore DF, Spark underscore DF equals PDF dot TO underscore Spark. 5. Identify how to import and use the Pandas on Spark a piece typical. Import PySpark Pandas as PS, then use PS dataframe, etc. Pandas UDFs function a piece 1. Identify Apache arrow as the key to Pandas less than dash greater than Spark conversions arrow, a columnar in memory data format that helps reduce serialization overhead. 2. Describe why iterator UDFs are preferred for large data reason. Iterator UDFs process batches of data iteratively, reducing memory usage and enabling better scaling on large data sets. 3. Apply a model in parallel using a Pandas UDF typical approach. At Pandas underscore UDF, return type equals doublet type, def predict underscore UDF, iterator, PD. Dataframe, dash greater than iterator, PD. Series, model equals. # broadcast or loaded for PDF in iterator, yield model.predict, PDF. 4. Identify that Pandas code can be used inside of UDF function. Benefit: reuse existing Pandas-based logic or scikit-learn calls in a distributed manner. 5. Train/apply group-specific models using the Pandas function API group-based. Use GroupMe. Apply in Pandas to train specialized models per group or apply group-specific transformations. Section 4. Scaling ML models. Model distribution. 1. Describe how Spark scales linear regression mechanism, uses distributed gradient-based or closed-form solution (LBFGS) or normal equations with data sharded across executors. 2. Describe how Spark scales decision trees mechanism, distributed histogram-based approach across partitions, merges histograms to find splits, and builds the tree in parallel. Ensembling distribution. 1. Describe the basic concepts of ensemble learning. Ensemble combines multiple base models to produce a stronger predictor. Examples: bagging, boosting, stacking. 2. Compare and contrast bagging, boosting, and stacking. Bagging trains multiple models in parallel on different samples of data, averages or votes predictions. For example, random forest. Boosting trains models sequentially. Each new model tries to correct errors of previous ones. For example, gradient boosted trees, XBoost. Stacking trains multiple models and uses a meta model to combine predictions. Part 2. Expanded additional topics. Below are additional or updated topics reflecting an extended exam scope, including MLOps strategy, Unity catalog-based feature store tables, expanded model deployment, and more. Section 1. Databricks Machine Learning. 1. Identify the best practices of an MLOps strategy. Key themes: version control, code, data, models, CI/CD automation, reproducibility, environment consistency, monitoring in production. Recommended reading, Databricks documentation on Millflow Model Registry plus DevOps. 2. Identify the advantages of using ML runtimes. Advantages: pre-installed popular ML libraries, optimized for performance, tested compatibility, GPU support for deep learning. Implications: faster experimentation, reduced environment setup overhead. 3. Identify how AutoML facilitates model feature selection mechanisms, automated search over algorithms, for example, linear versus tree-based, hyperparameters, and often feature transformations, normalization, encoding. Outcome: produces top-performing model pipeline, reduces guesswork for new ML practitioners. 4. Identify the advantages AutoML brings to the model development process. Benefits: speed, baseline model creation, consistent methodology, comprehensive experimentation. Considerations: may require domain knowledge to refine final model or interpret results. 5. Identify the benefits of creating feature store tables at the account level in Unity Catalog in Databricks versus at the workspace level. Account level, access control across multiple workspaces, global discoverability, centralized governance. Workspace level, simpler setup for small teams or single project usage, but less flexible across multiple projects. 6. Create a feature store table in Unity Catalog process, similar to creating a standard feature store table, but specifying the catalog.schema.table format in the name. Permissions: must have Unity Catalog privileges to create or modify tables. 7. Write data to a feature store table. Typical: fs equals feature store client fs.write underscore table name equals catalog.schema.features underscore table df equals features underscore df mode equals merge # or append overwrite. 8. Train a model with features from a feature store table workflow. Create a feature lookup object, specify primary keys, point to the Unity Catalog path for the table, then join the features into your training set. 9. Score a model using features from a feature store table. Inference, similar to above, but typically you have a data frame of entity IDs, for example, user underscore id, then use the feature lookup to join features for real-time or batch inference. 10. Describe the differences between online and offline feature tables. Offline, typically stored in a data lake or warehouse, used for batch scoring and training data. Online, low latency storage, for example, Redis or Cassandra, used for real-time inference. 11. Identify the best run using Millflow Client API. Same approach, search underscore runs, filter or sort by a metric, pick the top run ID. 12. Manually log metrics, artifacts, and models in a Millflow run. Same pattern as before, ensuring traceability of everything from code versions to data versions. 13. Identify information available in the Millflow E tabs, run details, metrics, parameters, tags, artifacts, model registry, versions, stages, pending transitions, activity log. 14. Register a model using the Millflow Client API in the Unity Catalog registry key, model underscore URI equals runs, / run underscore id / model, name equals catalog.schema.model underscore name. 15. Identify benefits of registering models in the Unity Catalog registry over the Workspace registry. Benefits: central governance, cross-workspace collaboration, fine-grained access controls, unity of data plus models. 16. Identify scenarios where promoting code is preferred over promoting models and vice versa. Promoting code, often for large refactors or new feature sets. Promoting models, more straightforward for small changes in parameters or incremental improvements where the pipeline code remains stable. 17. Set or remove a tag for a model. Millflow client.set underscore model underscore version underscore tag name version key value client.delete underscore model underscore version underscore tag name version key. 18. Promote a challenger model to a champion model using aliases. Aliases, a stable pointer for champion versus challenger. Use them to easily swap which version is champion without changing code references. Section 2. Data Processing 1. Compute summary statistics on a Spark data frame using summary or Butels data summary. Same as the original outline. Make sure you know both approaches. 2. Remove outliers from a Spark data frame based on standard deviation or ICR. Implementation. Broken vertical bar standard deviation. Mean. K asterisk def. Mean plus K asterisk def. Broken vertical bar ICR. Q1-1.5 asterisk ICR. Q3 plus 1.5 asterisk ICR. 3. Create visualizations for categorical or continuous features. Databricks tools. Built-in display function for histograms, box plots, bar charts. Pandas on Spark. Plot kind equals hist slash bar. 4. Compare two categorical or two continuous features using the appropriate method. Two categorical, chi-square test, contingency table. Two continuous, correlation, Pearson, Spearman, scatter plots, regression analysis. 5. Compare and contrast imputing missing values with the mean or median or mode value. Same coverage as the original outline, but also consider domain context. 6. Impute missing values with the mode, mean, or median value. Spark ML. Use imputer. If mode is needed for categorical, you might do that manually or convert the feature first. 7. Use one-hot encoding for categorical features. Same coverage. String indexer plus only hot encoder. 8. Identify and explain the model types or data sets for which one-hot encoding is or is not appropriate. Linear models that rely on numeric expansions. Potentially not necessary. Tree-based models or those that can handle categorical variables directly. 9. Identify scenarios where log scale transformation is appropriate. Scenarios, highly skewed continuous data, multiplicative relationships, or data that grows exponentially. Section 3, Model Development 1. Use ML foundations to select the appropriate algorithm for a given model scenario. Conceptual, classification versus regression versus clustering, interpretability versus accuracy needs, data volume and dimensionality. 2. Identify methods to mitigate data imbalance in training. Data methods, oversampling, SMOT, undersampling, class weighting, synthetic data generation. 3. Compare estimators and transformers as in Spark. Estimator, fit method, transformer, transform method. 4. Develop a training pipeline, series of transformations, data cleaning, feature engineering, plus final estimator. 5. Use hyperopts fmin operation to tune a model's hyperparameters. Syntax. Fmin fn equals objective underscore function, space equals search underscore space, algo equals tpe dot suggest, max underscore evols equals, trials equals. 6. Perform random or grid search or Bayesian search as a method for tuning hyperparameters. Key, understand how each approach works. Pros cons, computational cost, coverage of parameter space. 7. Parallelize single node models for hyperparameter tuning. Spark drills distributes each trial to an executor, enabling faster search for single node algorithms. 8. Describe the benefits and downsides of using cross-validation over a train validation. Split covered above. More robust versus more expensive. 9. Perform cross-validation as a part of model fitting implementation. Spark's cross-validator. Scikit-learn's cross_val_score, etc. 10. Identify the number of models being trained in conjunction with a grid search and cross-validation process. #param combus times #CV folds. 11. Use common classification metrics. F1, log loss, ROC/OC, etc. F1, good for imbalanced classes. Log loss, probabilistic measure, penalizes confident wrong predictions. ROC/OC summarizes performance across thresholds. 12. Use common regression metrics. C, may, R squared, etc. C penalizes large errors more. May gives linear penalty to errors. R squared, proportion of variance explained. 13. Choose the most appropriate metric for a given scenario. Objective classification. If class distribution is imbalanced, prefer F1, OC. For general classification, accuracy might suffice. Regression. If outliers matter, consider may or C. 14. Identify the need to exponentiate log transformed variables before calculating evaluation metrics or interpreting predictions. Covered earlier. 15. Assess the impact of model complexity and the bias variance trade-off on model performance concept, overfitting versus underfitting, how to interpret learning curves. Section 4, Model Deployment 1. Identify the differences and advantages of model serving approaches, batch, real-time, and streaming batch, large volumes, scheduled or triggered, real-time, low latency REST endpoints, streaming, continuous data processing, for example, Kafka, Delta Live tables. 2. Deploy custom model to a model endpoint Databricks model serving. Create a serving endpoint from the model registry version. Custom, use MLflow models plus Docker containers. 3. Use pandas to perform batch inference approach. 1. Load the model, for example, mlflow.sclearn.load_model. 2. Apply model.predict on a pandas data frame. 3. Write results back to storage. 4. Identify how streaming inference is performed with Delta Live tables concept, real-time data pipeline where each batch or micro-batch triggers the model scoring step, then results are written to a sync Delta table, Kafka. 5. Deploy and query a model for real-time inference Databricks serving. Create an endpoint in the IE, provide a name, select the model version. Then query via REST with an input. 6. Split data between endpoints for real-time inference scenario, /B testing or canary deployments. Route a portion of traffic to a new model endpoint, compare performance, then scale up if results are good.
If you found this guide helpful, please share it and don't hesitate to let me know if you would like to see more content like this for other certifications. I have no plans for monetizing this channel, even in the future. I do it simply to help others. But hearing your feedback genuinely motivates me to keep going. Good luck on your journey to become a certified professional. Thank you.